Hello everyone! Welcome to David Griffiths Electrodynamics. This is going to be problem 4.6 from the book. We're going to go ahead and read our problem statement here. So we have a perfect dipole P situated at distance z above an infinite grounded conducting plane. The key word here is going to be grounded. So that means the potential is going to be 0. The dipole makes an angle theta with the perpendicular to the plane. Find the torque on the dipole P due to the basically due to the field that's going to be created on this conducting plane. If the dipole is free to rotate, what orientation will it come to rest? Okay, so let's talk through this problem setup here. I'm going to move the book to the side. Okay, so we have a dipole P located some distance z above this plane. So I'm just defining the z axis this way. You could define, I guess I'd define this one as x. You could define it as y. Doesn't matter. I guess really y makes more sense if we're doing a right-hand coordinate system, but whatever. Okay, not really going to be a huge deal for this problem. So it makes this angle theta with the z-axis. This could be any angle. And yeah, we had this pure sort of dipole here. And I kind of exaggerated the dipole, so I'm just denoting that there's a negative charge here, a positive charge here. Really, a pure dipole, though, is like a point sort of dipole. Now, if you think about what's happening here, this dipole, of course, produces electric field. And this is a conducting plane. So, on this conductor, the charges are kind of free to move. So what's going to happen is the charges on this conductor are going to orient themselves, are going to start moving around until they reach some kind of equilibrium due to the charge. So this dipole is going to induce some kind of surface charge on this conductor to sort of match the charge until all the charges come into some kind of equilibrium with the force applied to it. And then what happens is that field, that's going to create some kind of electric field that the conductor now is creating, because now there's some non-zero distribution of charges on the conductor, and that electric field is going to produce and affect the dipole and cause a torque on the dipole. So our job is to find what is the torque produced on the dipole. The problem is we don't know how these charges are going to be distributed. We don't know anything about how these charges will distribute themselves. We don't know how much charge it is. We don't really know anything about how these charges are going to distribute, which means it's going to be very hard for us to figure out what the potential or what the electric field is produced by it, so that we can find the force and so that we can find the torque on the dipole. So, to find the torque, we need the dipole moment, which we have, but we need E. Now, your brain should start going back to the methods that we derived in chapter 3 for how to find electric fields and potentials and things. So, solving Laplace's equation might work, but, it would be a lot of work, probably, and we don't really know anything about the distribution of the charges here. But yeah, you could maybe solve Laplace's equation in this region or something. But another method is that the fact that this conducting plane is grounded, the potential is 0, there's a theorem that we come up with in chapter 3 that says, if a potential, if some configuration of charges, meets the same boundary conditions and stuff, and potential and things in the region that you're solving for, then that potential is correct. So essentially, let me go back to chapter 3 and see if I can find it. But it's essentially like the uniqueness theorem. It's like the second uniqueness theorem. Yeah, it says the simplest way to set, let's see. We have conductors, okay. There are circumstances in which we do not know the potential at the boundary, but rather the charges on various conducting surfaces. Okay, here we go. In a volume V surrounded by conductors and containing specified charge density, the electric field is uniquely determined if the total charge in each conductor is given. Maybe it's actually the first uniqueness theorem. Yeah, actually, sorry, it's the first. It's this boundary conditions and uniqueness theorem. So the solution to Laplace's equation in some volume V is uniquely determined if V is specified on the boundary surface S. So if we can come up, essentially this leads into the method of images, where you basically learn that if you can figure out a equivalent problem setup that has the same potential at the boundaries, same boundary conditions and everything, and no extra charge or anything is in the region that you're actually interested in, then the potential produced by that new problem has to be the same as the potential produced by your old problem, essentially. There's one unique solution for Laplace's equation by some given set of boundary conditions. So what we can do here is use the method of images to replace this conducting plane that has a potential 0 here with essentially an image dipole. So essentially what I'm going to suggest is that instead of a conducting plane here, we want to have another dipole down here below the plane that, if placed in the correct location and oriented correctly, it would produce a 0 potential at the plane location, just like the conducting plane has, and no extra charge up here. The only charge, the image is going to be down here. And if that's the case, if you can figure out a configuration that can do that, then the solution to the potential and everything should be exactly the same as the conducting plane situation. So we know that, like, if we have this dipole, it's producing a potential of this P1 dot r hat over 4 pi epsilon naught r hat r squared. You know, let's just say we're finding the potential at the conducting plane here. What we want then is another dipole down here that at that same point would add up and cancel out the potential of the real dipole to give 0 potential anywhere along this plane. So what we want is V1 is the potential of our real dipole. V2 would be the potential produced by the image dipole. So what we want is V1 to be V1 plus V2 to be 0, which means that we want, so V1 needs to be negative of P2 dot R2 over 4 pi epsilon naught R2 squared. Now, to get this situation, if you just look at like R1, this vector R1 and R2, clearly the x components of these two vectors will be the same, right? Like if we place this one at an equal distance z down here, it's going to have the same x component of the vector, right? If we draw out these components. So to get a negative sign, what needs to happen then, and we're just looking at a 2D situation because the phi direction really doesn't matter here. We're just kind of looking at this from a plane. So to get a negative sign here from the script r, we're going to need, and this dot product, right? The dot product is going to be P2 dot R2x, or sorry, P2x R2x plus P2y R2y plus P2z R, whatever, like, right? That's going to be the dot product essentially. So to get this negative sign, what needs to happen? Well, the x components are going to be the same, so that's not going to give us any kind of negative. The z component, though, if we flip the z component, meaning like the dipole was going down or pointing downwards, I guess, then it would have a minus, there would be a minus sign there which would negate with, let me just think here. So R1 and R2 clearly will have the same x components, so the negative relationship will come from their opposite z components. So our image dipole needs to have the same z component as the real dipole, but it needs to have opposite p sub x components. So essentially what I'm suggesting here is that if we orient this dipole, the same distance z here, but the dipole is going to be oriented this way, then the x component here is going to be opposite of the x component here. The z component will be the same. And that will give us the negative sign. Because if the z component was flipped also, we'd have a negative and a negative, which would be positive, and we don't get this negative sign when we do this dot product. So the only way we're going to get this negative sign is if we have one of the components flipped and one of them the same. So we're gonna flip around the axis and have our dipole oriented this way with an angle theta like that. And that sort of configuration should give us a potential of 0 along this plane. I don't know how convincing that is, but it's convincing enough for me to go ahead and proceed with the problem. But if it's not convincing enough to you, I suggest really doing the math here and trying to dot out all these components and just kind of see how you should orient that image charge to give you that negative relationship there to make sure you have a 0 potential. So this is our problem now that we're going to solve instead of the conducting plane problem. But what's nice about this is we know the electric fields of dipoles and we know the potentials of dipoles and stuff. So we can use this to our advantage to solve for the torque, and that will be equivalent to what the torque produced by the conducting plane would be, which is really cool. So we know that the electric field produced by the image dipole is P over 4 pi epsilon naught, R, or like the distance between the two, which in this case is 2z, because this distance is z to the origin plus another z. So I write 2z cubed, right? That's really r cubed, but I'm replacing that with 2z. And we have 2 cosine theta r hat plus sine of theta theta hat. And this is just equation 3.103 from the book. So we've been using this equation for the electric field of a dipole for a while now. And then if we just shift our coordinate system, so if we kind of move our coordinate system down to where it's like, if we shift the coordinate system down to where now our origin is at the dipole, and then we rotate it to where P2 is now pointing up, you kind of get this sort of situation. So we now have, I'm just doing it like this. So if you imagine we rotated, then by the angle theta, then now this one would be oriented, slightly differently. Still an angle theta from this line, but essentially you just got to think about how I shift this. I just move the origin down, rotate so the image dipole is pointing upwards, and this line still connecting the two is still 2z. But anyways, I do this so that to get the torque, we need to know we need this expression for. We have the expression for the electric field. We just need the expression for the dipole moment of P1, which we can just write as P cosine theta r hat plus P sine of theta theta hat. It's just going to have the dipole moment's going to have r hat components and theta hat components, no phi hat components, because it's spherically symmetric about phi hat. And then we can use this expression for the dipole moment of P1 inside of the torque expression. So doing this cross product, we end up getting P squared over 4 pi epsilon naught 8z cubed And then we're going to have just pulling out the P here, and then you will have the P from the electric field. So that's where the P squared comes from. And the 8z cubed, of course, is just cubing that bottom term. So then the cross product is going to be cosine of theta r hat plus sine of theta theta hat crossed with 2 cosine theta r hat plus sine of theta theta hat. So you got to do this sort of cross product here. Of course, a vector crossed with itself, so like r hat cross r hat is going to be 0. Theta hat plus theta hat is going to be 0. So you're just going to have the cross terms. And so r hat crossed with theta hat is going to be phi hat, and theta hat crossed with r hat is going to be minus phi hat. So if you do those cross products, you get p squared over 4 pi epsilon naught 8d cubed. Then you have cosine theta sine of theta phi hat plus 2 cosine theta sine of theta minus phi hat. So this is really just cosine theta sine of theta minus 2 cosine theta sine of theta. So that would just be minus 1 cosine theta sine of theta. So then what we have here for our final torque is p squared sine theta cosine theta over 4 pi epsilon naught 8z cubed with the minus phi, and I put the minus sign with the phi hat just to kind of denote what direction that is. And then using a trig identity, you can also rewrite this as the fact that sine of theta cosine theta is the same as 1/2 sine of 2 theta. And so you can get this little expression here. So the torque is p squared sine of 2 theta over 4 pi epsilon naught 16z cubed because of the 1/2, the extra 1/2 term here in the minus phi hat direction. And then the problem asks us at what orientation will the dipole reach an equilibrium? So that's essentially asking at what point do we have a stable, equilibrium for the torque. So essentially, where does the torque equal 0? At what orientation does the torque? Is there no net torque? So our really only variable here is theta. So theta is going to be 0 when we have pi over 2, pi or 0. So 0 or pi, any kind of multiple pi essentially is going to give us 0 for sine, which would then give us 0 for the torque. So if you look at our original orientation in our problem, we defined theta like this. So 0 would be when the dipole is pointing just straight up on the z-axis, or pi is when it's pointing down on the minus z-axis. So essentially we get a nice stable equilibrium when it's pointing up or down along the z-axis, and any offset from that, we're going to have some torque that's going to try to restore it to align with the z-axis essentially. All right, so that is problem 4.6. If you guys have any questions, comments, or concerns, feel free to let me know in the comments below. Like always, leave a like, subscribe to my channel if you haven't already. If you'd like to become a member of the channel, you can get access to early access to my videos, as well as getting full LaTeX solutions, typed up LaTeX solutions of all these problems as well, for a higher tier membership. But like always, hope you guys have a great day, and I will see you guys on the next video.